All right, so we're going to talk about a more advanced topic in Lewis structures now, and that is formal charge versus expanded octet. Sometimes it's easy to get rid of formal charges by expanding an octet. You can't expand octets for certain atoms, but for third period and lower you can. And so if we have something like this, this is 4 groups, has 4 single bonds to it. And so the OPCL angle should be about what? The OPCL angle should be about what? 109. The OPCL angle should be 109. The CLPCL angle should be 109. 109. It's the shortest angle. This is tetrahedral geometry, right? The tetrahedral. And so this looks good. The only thing that doesn't look so good about this structure is the formal charge. When we look at the formal charge on oxygen is minus, the formal charge on phosphorus is plus. So one of the things that's commonly done with something like phosphorus can expand its octet. You know, it has those d orbitals. And so what we can do is we can throw in some extra electrons into the d. And that is, we'll create a double bond with the oxygen here. If we create a double bond with the oxygen, then the formal charges all go to 0. Not only that, it seems like we're maximizing the bonding interaction because, you know, double bond is stronger and shorter than a single bond, right? And so all in all, this looks like a good plus because here, you know, we're expanding the octet. And we saw phosphorus has no problem expanding the octet, right? Look at PCl5. But there is some debate about this. And so I need to tell you about the debate about this. The debate about this is some people say, no, you cannot go beyond an octet. If you can't go beyond an octet, then we're stuck with this structure here. And we're stuck with a single bond, but this is not just a single bond. Because these charges are real, because this oxygen has an extra electron, this phosphorus is missing an electron. And so not only do we have a covalent bond, but in addition to the covalent bond, there's an ionic interaction. This is not like the percent ionic character we were talking about earlier, you know, with bond polarity. This is an actual ionic bond with a full charge on this oxygen and a full charge on the phosphorus. And so the negative is attracted to positive, that's called an ionic bond. So there's 2 bonds happening between phosphorus and oxygen. The covalent, the polar covalent bond here, certain percent ionicity, and an actual ionic bond. And that's going to make this phosphorus-oxygen bond stronger than a normal single bond and shorter. And so we can maintain an octet, or we can expand an octet. If we expand the octet, then we have to take advantage of the d orbitals, put the extra electrons into the d. But we have this double bond here, which is quite nice. You might say, well, why don't we just expand the octet like PCl5? Well, the same thing happens with PCl5. Remember PCl5, we had 5 covalent bonds to that, all polar covalent bonds. But some people are saying, no, PCl5, you can't go beyond an octet. If we can't go beyond an octet, then what we have is we have 4 chlorines bonded to phosphorus, like this. When we have 4 chlorines bonded to phosphorus, it leaves a positive charge on phosphorus here. And then we're going to have a chloride out here. The chloride's going to have a negative charge like that. And so essentially the bonding picture here is we have 4 covalent bonds that completes its octet. The way we can stick the 5th chloride on there is by forming an ionic bond. I'm just going to hold it there. All right, now the structures of these, what's the structure of this? This is going to be tetrahedral. Now the OPCl angle is going to be distorted because we have a double bond here. You know, this we don't expect much distortion, although the atoms are different. Chlorine's bigger than oxygen, so there are going to be slight distortions, but nothing significant, nothing that we have to talk about. Here, there's going to be a more significant distortion because of the double bond. So this should be 107. This should be about 111. Here. Now, something like this, how is this going to distort the structure? Well, this doesn't really distort the structure because what we can do is we can draw 5 resonance forms for this. And so rather than having the chloride out right, we can put the chloride up over here. And so we have 5 different positions for the chloride. And so what we can do is we generate 5 resonance structures for this, and then we get the hybrid. The hybrid is going to smear out the negative charge throughout all chloride. So each chlorine would be a -1/5 in the resonance. And there'd be some ionic and covalent character in each bond. All right, so when you look at the literature, most people represent OPCl3 like this. And so this is generally the accepted structure where we did expand the octet. But more recent evidence is suggesting there's not much d orbital participation, and there's much more ionic contribution. And so more recent evidence is maybe leaning towards this. And so the point is, it gets more complicated as we go along. All right, now we'll look at something more involved than these structures here. We're going to look at ClO4 minus. ClO4 minus, because chlorine is the central atom, and it's going to be bonded to 4 oxygens. So we got a chlorine bonded to 4 oxygens. Complete the octets on the oxygens. I'm not going to draw it 3D. What's the geometry of this? Tetrahedral. I'm just going to leave it like this to save time. So this would be tetrahedral. Everybody has an octet, so everybody's happy. Or are they? Well, what we should do is we should take a look at the formal charges. And so when we take a look at the formal charges, we'll see the formal charges on all the oxygens are negative. And the formal charge on chlorine is +2. Actually, +3. Sorry, not +2, +3. And so when we sum up all the formal charges, we'll get the net charge on the ion. The net charge on the ion is -1. All right, this is having an octet, but do you see this is the same thing as we said before? We have an octet, but we have all these charges. And if we leave the charges there, there's going to be some ionic component to this, but those are high. I mean, +3, chlorine losing 3 electrons, does it seem very likely? No, I1, I2, I3, no, not very likely. And so what's commonly done with a structure like this, we'll call this structure series 1, is we'll expand the octet. And so let's expand the octet by 1 bond. So we'll put a double bond here, take a lone pair off this oxygen and bring it to the bond. And then we'll end up with four single bonds like this. And that's going to drop the formal charge. Now this oxygen's 0, these 3 oxygens are minus, and now chlorine's +2. Well, +2 is a heck of a lot better than +3. Right? But we had to expand the octet because now we have 10 electrons in chlorine. But that's okay. One of the things that can happen is there are going to be resonance forms for this. And so here we have one resonance form. The other resonance form is we leave the atoms in position and just move the bond. So we'll move the double bond from the top here. Maybe we'll just bring it left here. So put the double bond to the left. Generates this structure. And then we have the negative formal charges here, the +2 charge, and again, We're going to have a net plus, net negative charge here, -1. How many more resonance forms can I draw? Well, I can move the double bond from here to here, and then from here to here, and then from here to here. So there are going to be 2 more resonance forms I can draw. And so let's drop the double bond down here. There's going to be single, single, and single. And then one more possibility. All right, the actual structure is going to be a composite of all 4 resonance forms. That's going to be the hybrid. And so the hybrid, we're going to have a single bond fixed to each oxygen. And so we'll have a chlorine here, 4 single bonds, the oxygens. And that double bond is going to be smeared out over the 4. And when we smear it out, it's called delocalization. So we just spread out the electron density over all 4 bonds here. Well, that's not much electron density to spread out. And so when we have something like this, 1 double bond spread out over 4, then it's going to be 1 bond, 1 extra bond in the 4 positions. And so it turns out the bond order for this is going to be a 1.25 bond. And so each bond is the same. It's 1 1/4 bonds. In other words, we have a total of 1, 2, 3, 4, 5 bonds over 4 positions. So that's 5/4. 5/4 would be 4/4 plus 1/4. 4/4 is 1, so 1 1/4. So each of the bonds are exactly the same. They're close to a single, closer to single than a double. No, it was 1 1/4. And then we look at the lone pairs. There are 2 lone pairs fixed all the time, and a 3rd lone pair that floats. So let's draw 2 lone pairs that are fixed. This 3rd lone pair, actually two lone pairs are going to be floating, delocalized over the 4. And so we have a -2 charge spread out, actually -3 lone pairs spread out over 4. And so we have a -2 charge, -3 charge, -3 charge spread out over 4 atoms. -3 charge spread out over 4 atoms gives each one a -3/4. -3 over 4 is -3/4. And so that's the formal charge on each of these, -3/4. And so if I times it by 4 for the 4 oxygens, I get -3 total net negative charge. And then the chlorine's +2. It's fixed. And so this is going to be octahedral, right? The OCl-O angle is going to be at 109. Okay. This is going to be series 2. But, you know, in this case, we still have that ionic interaction, but more covalent. Yeah. We can lower the formal charge even more by forming a 2nd double bond. And so if we form 2 double bonds rather than 1 double bond, then we'll have 2 doubles and 2 singles, like this. The formal charge on these oxygens here would be 0. Formal charge on these 2 would be negative. And the charge on chlorine now is only +1. The formal charge is getting a lot better. Still adds up to a total of -1. And so we have 2 double bonds now. How many resonance forms can we draw for this? Well, the easiest is, you know, to leave the atoms in place and then just move. Let's just move one of the double bonds first. And so we'll leave the top double bond fixed for right now, and then move this one down here. So we end up with this structure. I'm not going to draw out everything. Just up like this. Okay, so if we leave the top one fixed, then we can move the double bond to the right. And we end up with this structure. I won't complete it. You complete it. Is that it? No, that's not it, because what we can do is we can move the top one. Let's move the top one. And so we'll leave the one on the left here from the first one, and then move the top one. So we'll just have it going left and down. And so we'll have longer ones here. But didn't I just draw this? Isn't this structure here? If I take this structure and just flip it like that, aren't they the same thing? No. What we do when we do resonance forms is we leave the atoms fixed and only move the electrons. And so if we leave the atoms fixed and move the electrons, this is a different electron distribution than any of those. And so this is a unique resonance form here. Is that it? No, because we could leave this one on the left as a double and then make this one on the right a double, and then two singles, one up and one down. Is that it? No, because if we leave this one on the right, then we can have one going down. So that makes the singles like this. Now, is that it? Is that it? Yeah, this is it. And so I could fill in the rest and write the formal charges out, but there are going to be 6 resonance forms. And so what's a hybrid going to look like for this series? We'll call it series, so that's 3. This is structure 3. The hybrid for structure 3 is going to look like this, where we're going to have 4 single bonds fixed permanently, but now we're going to spread out 2 double bonds over 4 atoms. 4 bonds. So we're going to delocalize that. And so we spread out these 2 double bonds all over 4, so that's 2 double bonds in 4 positions is 1/2, or 2 over 4. And so the bond order for each of these is 1.5. It's a 1.5 bond. It's halfway between a single and a double. And the charge, we have -2 total negative charge over 4 atoms. -2 over 4 is -2/4 for each. -2/4 is -1/2. So each of these oxygens is -1/2. The chlorine charge is fixed. You know, the chlorine's charge doesn't change in all these structures. And chlorine's just +1. And so the net charge on this altogether, actually the lone pairs, we're going to have 2 lone pairs fixed on each. And then we're going to have some electron density spread out over 3. Like that. And so this is the hybrid structure for these 6. These are 6 degenerate forms, and those are all the combinations. If we don't move the atoms, we just move the electrons. That's it. So this hybrid 3, this is hybrid 2. Hybrid 3 looks better from a formal charge perspective, but from an expanded octet, it's kind of getting up there, because now we have 2, 4, 6, 8, 10, 12 electrons. We're expanding the octet significantly. Well, I just want to keep going and expanding the octet. And so this is number 3. Let's go to number 4. I'm going to try to get rid of the formal charge as much as possible. And so what I'm going to do is I'm going to go for 3 double bonds. Three double bonds has the advantage of dropping all the formal charges to 0, except for this oxygen, which has a negative formal charge. And so that's looking good, except look how much we expanded the octet now. 2, 4, 6, 8, 10, 12, 14 electrons. I mean, is it unlimited how much I can expand the octet, or is there some kind of limit? Am I pushing it? Am I pushing the envelope, or do I have plenty of room? Seems like I have plenty of room, but there is some cost to expanding the octet. And as I expand it more and more, that cost is growing, right? But anyway, I'm just going to continue with the structure, and resonance forms are possible for this. Because here I have the, well, here it's easier to look at the single bond. Here the single bond is to the right. Let's make the single bond go up. If I make the single bond go up, then double bonds are going to be here. That's another one. If I make the single bond go to the left, then the double bonds are over here. That's another one. And if I make the single bond go down, the double bonds are here. And so in this structure, I'm going to generate a total of 4 resonance forms. When I come up with the hybrid structure is going to have single bonds permanently affixed to this. And then I'm going to have, the easiest way of figuring out the bond order is to do this. Double bonds counted as 2, so 2, 4, 6, 7. A bond order is 7 divided by 4 positions, and so that's 7/4. 7/4 would be 4/4 plus 3/4, so 1 3/4. And so the bond order is going to be 1.75 each. Or 1 3/4. So I got some electron density spread out here, 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 and here. And so it's a 1 3/4 bond. And then there are 2 lone pairs fixed. And 1 lone pair spread out. And so here I have a -1 charge spread out over 4 oxygens. A -1 charge spread out over 4 oxygens is -1/4. And so each oxygen has a -1/4 charge. And the chlorine's 0. And so when I add up all the formal charges, they total -1. And so from the perspective of formal charge, this is the best structure. From the perspective of the octet and the cost associated with it, expanding the octet, then the first structure is the best. And so which structure is most accurate? Because this one doesn't rely on any ionic type bonding interaction here. It's all covalent, polar covalent. And so the reality is the structure is somewhere in between these. Because we're going to have different contributions depending on the stability of this. You know, how big of a contributor is structure 4? Well, with structure 4 with 3 double bonds like this, creating 3 double bonds at this geometry is going to cost some energy. And so structure 4 might not be a big contributor. And so what we end up doing is we end up making a hybrid of hybrids. Each hybrid, or each one of these series, will contribute some percentage to the overall structure. The reason we're doing this is because we aren't doing any calculations. You know, when you do calculations, electron density is there and spread out. And we see how it spreads out. All right, so this is a complicated case here. And so what do you do in situations like this? Well, what people do in situations like this is just draw all of them and say the actual structure is going to be some kind of hybrid of hybrids. Okay? It's not going to be series 1, 2, 3, or 4, but all of them combined, weighted to some kind of percentage based on their stability. Okay? I'll stop here.